Let's go. All right. So we are going to apply what we did yesterday. So we used definite integrals, which is about integrating from one place to another, right? So I did briefly mention this yesterday. Now we're going to do it. So if I want the integral of 3x squared with respect to x, and I want it between 4 and 6, right? That's what we were doing. We were finding the area under a curved space. So what I'm doing here is finding the area under this graph with respect to the x-axis. Okay, that's the application of what this finds. So we already know how to do this, right? What we're just doing is now saying that is the area under the graph. So tell me what I do first. Integrate it. So what do I get? X cubed plus c. Do we need to do that when we're doing definite integrals? No, we don't need to do that when we're doing definite integrals. So what we're going to do is what? 6 cubed minus 4 cubed. You substitute in the big one minus the small one. If you put all that together, you get 152. And we just write it as units squared, right? Because we're not told if it's centimeters or something you're given, that's fine. But often we just get questions like this without a unit. Yeah.
Why are we just like integrating the equation of the graph?
As opposed to what?
Before we were doing it with
got you. So what we're really saying here is that, hang on. Yeah, no, this is what it is. So the integration, so when you're integrating derivatives, you're taking them backwards, right? So you've got the equation of the gradient and you're going back to the actual equation. If you take the derivative of the equation, sorry, if you integrate the equation itself, what you're then finding is the area of the graph underneath
what we were doing
the space.
Yesterday, or was yesterday?
Yeah.
Wouldn't help you find the area of the graph.
You'd have to do it again, right? So once you get back to the actual thing.
So technically we're finding the equation of the area.
No, you're finding the area.
No, but if
Or you mean that?
if we integrate it without then.
Yes, as long as that went on forever, yes. Whereas what we're doing is trying to take slices of it. Okay, so let's do one that's more complicated than just x cubed. Or 3x squared, sorry. Okay. Okay, I'm going to draw, this time let's look at a quadratic. Right, I'm going to draw you this. Can you have a go at doing this for me? Okay, so I would like, this is y equals x squared minus 6x. You should be able to tell me what the intercepts are by looking at this. What are the two intercepts? 0 and 6. Excellent. So I would like the area underneath the x-axis with respect to, right? So it's the area. So the way that you talk about it is the area bound by the graph and the x-axis. All right. So you are finding the area of the shaded region. And then we'll look at one that's a bit more complex. You're going to find something interesting with this, and I hope you can use logic to understand what it might be saying. Is that just my bad writing?
And the power of it allows in that same step. That was another.
My bad writing. All right. What is weird about this answer? It's negative. So we just ignore the fact that it's negative and we call it 36 units squared.
That's for the fun.
Correct, because area can't be negative, right? Why do you think we got a negative area? Because it's under the graph, right? If it was above the graph like the last question, it's positive. If it's below the graph, it's negative, but you just don't use negative numbers when you're talking about area. So take the absolute value of the area and just call it that. Okay? Okay. Yes. Oh, you don't need to put the symbol in, no. I'm just making a point.
That would be correct.
Yeah, absolutely. You don't have to for that. All right, so I am going to draw you a complicated one now.
At what point do you rate for the argument?
If it's negative, you just put it in at the end, right? I mean,
So
you don't have to write it in, but that is kind of the point. Yeah. All right. So this is y equals x.
Did we have a negative?
Okay, I would like you to have a look at this equation and tell me what you know about this graph. It's a cubic graph. What else do we know about it that I haven't labeled? Good, we know all the intercepts. X is going to equal 0, 2, and 6. So this gives us 0, this gives us 2, and this gives us 6. So we are going to find the area, the shaded area. I'm actually going to color these differently. Now, you cannot just find the area from 0 to 6. Based on what we just said, what do you think is going to happen if we just try and integrate from 0 to 6? Right, so this is going to be a positive area. This is going to be a negative area. And if we add those things together, we're going to end up with the wrong area, right? So what we're going to do is find out the area of them separately and then just add them together, right? You can't just integrate and have it all work out. There is a nice example in our textbook, which has sort of a graph that looks like this, right? Where these are equal sizes. And if you integrate the whole thing at once, you get 0 as your answer because they are going to cancel each other out. So we're going to work them out separately. So let's do the red one first. So we're going to integrate between 2 and 0, or 0 and 2, I should say. What do I need to do with this first? Yeah, let's expand it all. So we should get x cubed minus 12x squared plus 12. Sorry, that's not right at all. 8 minus 8x squared plus 12x. And we're integrating with respect to x. All right, so we're just going to do the red bit first. So what's my integral? Right, x over 4 minus 8 over 3x cubed. I'm just going to write it like that. Same thing, plus 6x squared, because it's 12x squared over 2, 6x squared. Now I substitute in my 0 and my 2. So I get 2 to the power of 4 over 4 minus 8 times 2 cubed over 3 plus 6, 2 squared. And I'm going to subtract. Now, do I need to write out 0? I don't need to write out 0. I'm not going to waste my time because all of these have an x in them. Or sorry, all of these have an x in them. So everything's going to be 0. So it's just minus 0. I'm not going to bother writing it out. You can just, anytime there's a 0 and there's no constant, you can just make an assumption that the whole thing is 0. Has somebody typed that into a calculator for me? Okay. No. It should be 6 2/3. Yep. All right, let's do the blue bit. So now we're integrating between 2 and 6 for the exact same function. So I don't need to integrate again. I'm just going to skip straight to this step, right? Because it's the same equation. So why bother doing it? I'm just going to say it's 6 to the power of 4 over 4 minus 8. Wait, what am I doing? 6 square cubed over 3 plus 6 cubed minus, and then I do the same thing with 2. So this time I can't just make an assumption. This is going to be 2. Although actually I do know this, don't I? I've already done it over here. I don't need to do it again. This is 6 2/3, right? Because that was 2 substituted in. So now I get all of that. If you type all of that into a calculator, you should have, so that's negative 36. All right. Now, with negative 36, I obviously have to now call it, well, let's not do it there. That is negative 36. So when I put them together, I'm going to add 36 to 6 2/3, which gives us 42 2/3 units squared. That is my area. The power's wrong? Where?
Oh, yeah.
Oh, there? Yeah. Okay.
Not that one.
Oh, that one.
Good.
Okay. Let's go back to blue. That should be cubed. That should be squared. Okay. Let's save that. All right. So that's really it. That's your application. Now, there's one more. Oh, actually, sorry. Let me just say one more thing. This is exactly the same as what we've just done, but you can do it sideways, but it's not different. It's the same thing. So if I give you a graph, I can draw a sideways equation as well. Oop, let's pretend that goes through the origin. Okay, so I'm going to ask you to find this area, but I'm going to give you an equation that uses y. Okay, so I'm actually going to say x equals y, 4 minus y. So what does that mean? You know about these values. So that's 0 and that's 4. So I'm just going to do the same thing, but I'm going to write it weirdly, right? So I'm going to say I'm integrating between 0 and 4. I'm going to just expand this. So I've got 4y minus y squared. And I'm now going to call this dy because I'm finding this in respect to y. But it's exactly the same. And now you just do exactly the same thing, right? So my integral is now 4y squared over 2 minus y cubed over 3. And then I just substitute in 4 and 0. So I've got 4, well, actually, this is just 2, isn't it? So let's do that. So I've got 2 to the power of 4. Why did I do that? Sorry. 4 squared minus 4 cubed over 3. All of that, subtract when there's 0, so I don't need to do anything because that's just going to be minus 0. And so if you type all of that into a calculator, you're going to get 10 2/3 units squared. So it's exactly the same. You just might have a dy instead of a dx. All right, I'm going to add one level of complexity to this. All right, so this is simply an application of exactly the same thing we did yesterday.